Okay, hello everyone. So this week's video is about something that just sort of came up while we were working, and it exposes a few mildly interesting elements of C++ and how it works. And I won't sort of try and describe it in advance. I'll just get in and show you what the problem is, and when we reach a bit which is sort of the question that we asked ourselves, I'll say where it fits in. Okay, so first of all, I'm going to do something that's not terribly complicated. I'm going to create a function that returns an object. In this case, I'm going to create a function that returns a vector of ints. And this is unremarkable. You can do it. So this is C++, just to be clear. I haven't said that, but it is. So I'm going to need to print some things. And I'm going to need a vector. Excuse me. So my function returns a vector of ints. Takes no parameters. And literally the only thing in it is I'm going to create a vector in there. I'm going to return it. Now, there is one question here that does sort of immediately perhaps ask a question. You know, normally you'd say, well, this is a variable here that's inside this function. Once this function exits, it doesn't exist anymore. So how can I return it? Well, the answer is because I'm returning the value. I'm not returning a reference to it or anything else. I'm not trying to keep a track of its memory. I'm going to return the object, and wherever I capture that object to is going to have this return value assigned to it. There's a slight wrinkle on that, which I'll mention when we come to it, but basically that's why this works. This object exists until this function is completely finished with, and part of that being completely finished with is the return value being copied into whatever variable captures that return value. Okay, so I'm now going to create my main, and it's not going to be very clever. Okay, what I'm going to do is I'm going to create a vector int variable, which I'm going to call demo. And I'm going to say demo equals get vector. Okay, and I'm now going to print the size. Oops, standard cout demo.size new line. Okay, so when I print that, I should just get this code runs and produces a number 0. It does nothing else interesting. And there we go, it is. And I can tell this has done something by I could do something like demo.pushback 15 here, which means I've now got one element in the vector here, but when I assign the vector that I return from this function to it, that element just gets thrown away. Correctly, but, you know, behind the scenes. No memory leaks, but it's gone. Whereas if I comment this line out, okay, I now have one item because I haven't done the assignment of the one I returned from my function. This one is newly created and it's empty. Now this is all fine, this works perfectly well, and it is correct per the C++ standard. Now, I will just mention, first of all, the thing that I said is sort of a wrinkle. So I take out this line with the pushback, okay? So I define demo here on one line, and here on another line, I set demo equal to get vector. You would think that if I just delete this and have it like this, it will be exactly the same. And in effect, it is. If I compile and run that code, it gives me the same answer. It gives me my 0 again. And that is correct. But behind the scenes, it's actually going to be doing something called copy elision, which we've mentioned before. We have a video on return value optimization and copy elision. But essentially, the point is it actually changes how that function works. In the previous version, where I have this line that creates demo, this line here with a semicolon, it's a semicolon, not a J, with a semicolon creates demo, and this line here assigns demo to now be the vector that's returned from this function, that's literally what it will do. It'll create this demo here. It may actually not, because I'm not doing anything else with it. But if I was doing something with demo here, it would create demo. Demo would be perfectly well defined. And then when you reach this line, it would actually call what's called the, well, either the copy assignment or move assignment, if you've got one, method of demo. And it will either copy or move the internal structure of the thing that's returned from this function here into demo. The whole point of the return value optimization is if I go back and make this all on one line, well, it knows that here, because it is all on one line, I'm both declaring demo here and defining its value here. Demo never exists on its own, so that copy is unnecessary. What you actually want to do is just literally create the vector that's returned from this function, this vector here. You want it to create it straight in the memory that we've got here. And that is actually an optimization the compiler does, and it's called copy elision return value optimization. It's not really terribly important here, but it does come into it slightly, so it's worth bearing in mind. As I say, we have a video on this. I'll find it and put it in the description. You can watch that if you're more interested in that. Okay, so now back to the key element here, which is what happens if I don't call this return? Just comment that line out. So the first thing that would occur to you is, well, I don't know. Something won't be right. You might think that this version with the copy elision would still assign it somehow to this, but it actually won't do that, because without this return, it doesn't know that it's meant to. So in fact, if I compile this, I'll get a warning first. No return statement in function returning non-void. And you might think, well, it's a warning. Warnings usually mean I can do it anyway. But if I compile it, on this machine, I can, and it actually works. On the machine where I tested this earlier, it didn't work, and it crashed. So this is being unhelpful. Let me see what happens if I split this back up here. I do demo equals get vector instead. Nope, it still works. Okay, this maybe if I try turning optimization on. Yeah, there we go. I'm now, when I turn optimization on, my print statement's just vanished. And this is one of the things. What I've done here, by not returning from a value from this function, is undefined behavior. We've mentioned undefined behavior before. And the thing with undefined behavior is once undefined behavior has been triggered, anything can happen. So the first behavior that I had, where I got exactly what I got when I wasn't invoking undefined behavior, that was perfectly okay, because it could do anything it wants. In this case, where I turn optimization on, it's clearly decided that it's one of the things compilers are allowed to do. They're allowed to say, you're not writing code with undefined behavior in it, because you guaranteed when you told me I was compiling C++ code that you hadn't done that. So it looks at this function and goes, actually, yeah, this function doesn't do anything. So therefore, this line's nonsense. Well, if this line's nonsense, well, these have to be, nonsense as well. So the whole code just gets optimized out. Which it's permitted to do, because once you've invoked undefined behavior, it's allowed to do whatever it wants. So this is the thing. You have a function, you return a value from it, everything works. You have a function, you do not return a value from it, nothing works at all. Now, the first question that would sort of spring immediately to mind, and it did to me when I first encountered this behavior, is, well, why is it only a warning? Why does the compiler only warn you? And the answer to it is, it's because of the fact that it may, for example, be that you know something the compiler doesn't and can't. So let me just put here another thing where I take an integer parameter to this function. And then I say, if I equals 1, return value. All right, then that's fine. I do it if I is 2 also. And now, actually, I'll do something a bit different. I could do the same thing, but it's ridiculous. I'll do value.pushback for return value. So in this case, there's now an integer parameter to this. If I pass it 1, I will get an empty vector. If I pass it 2, I will get back a non-empty vector. So if I change this to call them, it's still warning me though, but it now will work. And if I pass, instead of 1, I pass in 2, it'll still warn me when I compile it, but it'll work. If I pass in 3, well, it'll warn me, but it's now right. And so I don't get any output. So the point is, in this case, there is genuinely a path through this function that never returns a value. But the code works as expected so long as I stick to one of the paths that does. And this is the point. It only warns you because conceptually it says, well, you might know that I really can only ever be 1 or 2, and the code will never give it any other value. So why should I, as a compiler, or perhaps a one step back, why should we, as the people on the C++ standards body, say that you must write something that returns an object in a case where you know for a fact that case just isn't going to happen? Nonetheless, the compiler warns you because far more often than that situation coming into play is you really have forgotten to return from a function. And in fact, it's considered good practice nowadays, really was always, to always return a value from a function. Now, so I've now basically said something that you may or may not have known, which is if you do not return a value from a function that's supposed to return a value, you have invoked undefined behavior. Your code can produce nonsense, anything it wants, from working perfectly to not running at all, to producing complete nonsense, to producing plausible but wrong answers. So don't do it. But the question that then sort of came up with it was, well, what if there's an error inside your function? Well, if there's an error inside your function, then in C++, what you would do would be you would raise an exception, because that's what you do in C++ when there's an error. C++ handles errors through exceptions. So let's have a quick look at this. Now, the one thing I will say is you probably guess, well, of course, it's going to work. C++ uses exceptions. It's used in all kinds of big things. If you couldn't do something as simple as returning from a function, I should actually be clear here. I've said returning from a function. I'm going to make a distinction. When you encounter a return statement like this in a function, I'm going to say that at that point there is a return action, i.e. it triggers something that actually makes this line here that captures that return value actually happen. And whether that's by copy assignment or move assignment, as it would be on this line, or by that copy elision mechanism, somehow when this return line is reached, data actually gets moved into this variable here that you're capturing into, or printed to the screen if you're passing it to a cout or whatever. But whatever happens to that value happens after this return statement has been reached. There is a return action. On the other hand, of course, even if you call an exception inside, throw an exception inside a function, the function still exits, you still return from it, you jump to the function above the function you were in. Various automatic things to do with, the stack still happen. But this return action doesn't happen because that return action is triggered by this return statement executing. So we'll have to be a bit careful between talking about returning from a function in the sense of getting out of it and going back to the function that called it, and returning from a function in the sense of returning a value. Okay, so I'm going to include the header for the standard exceptions, and I'm now going to simplify this a bit because I'm not going to have two different things where it returns different things. I'm going to actually have it take that value that you pass in, the I, and you're actually going to push it into the array, and you're going vector, and you're going to return the vector. So this function now will always return a value. But I want it to not, if you say I equals 2, I want it to raise an exception. So runtime error. That's the one I want. It's the easiest one here. It's just going to say that 2 is not valid. So, and I have to throw that exception. So this code is now saying you pass any value you like to get vector, and that value will get put into a vector of ints, and that vector of ints will get returned to you unless you pass in 2, in which case it'll throw an exception. Now, if I now go down here, I can produce 2 versions of this, one which calls it with a value 3 and one which calls it with a value 2. So this is going to do nothing when you compile it, no warnings anymore, because it now always returns a value from inside the function. And when I run it, the first one works successfully and prints this 1. The second one then fails because of the fact that an exception was thrown. It tells me it was, 2 not valid, so it's my exception. But what about if in here if I use the try construction? So the entire point of try, of course, is I'm saying, well, try the lines in here, but if they don't work, do what happens in the catch section instead. So trap this exception and go into the catch. So is this going to be like not returning from the function? And, well, you might think it is because you're not returning a value. This throw does not have this return statement. It does not trigger a return action. And as I say, you can probably guess that the answer is no, because it would severely weaken the ability of C++ to actually use exceptions if it was true. But when I run it, you can clearly see that it isn't true. So what I've changed it to do here is it tries to do demo is get vector 2. If it doesn't succeed, just ignore, just do nothing. But then it prints the size of demo, and then it prints the first element of demo. And essentially what it shows is that this line effectively does not get executed unless this function succeeds. If this function throws an exception, then before this assignment on the left-hand side actually occurs and potentially scrambles the demo object, execution stops and jumps into this catch block in here. And so when I look outside here, demo is just unchanged. Demo is still what demo is from this line here that has succeeded. So that is fine, but there are some questions that sort of remain here, which is most notably, well, what about if you go back to that sort of return value optimization thing? So what about if I get rid of, let's get rid of these lines here, and this definition of demo, and I create my vector demo there, and I print its size and I print its first element there. This now can't work because, as I said, the whole point of the return value optimization of the copy elision is this thing doesn't exist. You don't need to create a valid empty vector of ints and copy this in. In fact, C++ nowadays requires that you do not. You just don't need to. You must not do it if you're a valid C++ compiler. So how can this work? Well, you'll see as soon as I compile it. Because it tells me demo was not declared in this scope. And this is something you're probably immediately going, well, of course, if you're an experienced C++ programmer. But scope is actually one of the things that confuses people when they're sort of learning and beginning with C++ quite badly. And it's actually something that, before finally explaining this, because it'll be fairly obvious once I have explained this, I may as well demonstrate the idea of scope first. So the idea of scope is effectively, for a given variable, simplifying rather a lot, for a given variable, where can you use that variable? Not just where can you use the memory, because with things like that's what's called lifetime. And with things like pointers and new operators and the like, lifetime and scope can be very different. Scope is about where you can use a particular name for a variable. So if you've not literally just started with C++, the fact that I could create an integer called myint here, but I can't use it in here, should be something you're familiar with. I define this variable here, myint, inside main. The fact that I put it inside main means that it only exists inside main. It does not exist inside getVector. And, I'll compile it just to show that it doesn't exist. And, if I instead were to put it out here, well, it exists in both places. There we go. Except I got rid of the line actually printing it, but if I hadn't, it would have... Oh, actually, just do that. Put that back. Not... Okay. We'll put in here, myint is 4. And then we'll do get vector 3, the version that doesn't trigger any kind of exception. Now, I will say this is one thing that not all languages do, but C++ does. In C++, it's perfectly acceptable to not capture the return value of a function. That's completely acceptable. Still still undefined behavior if you don't return from a function when you should, but it's perfectly fine to not capture that return value, and the compiler just takes that value and throws it away. In fact, it might optimize in some senses to have it never exist, but the rules on that are actually, I don't understand them myself. Okay, so what this thing will do is it will set myint to 4. It'll call getVector, which will do all the stuff it was doing before of creating a vector of ints, but we're then going to throw that away because we're not capturing it. But it'll also print myint, and then main will print myint as well. Okay, and it's 4 in both places. Now, because this out here, not inside any function, is in what's called global scope. Now, global scope is something you shouldn't really use in C or C++. It's very old-fashioned. It's actually also easy to use wrong. But global scope is available from any function. But the other thing about scope is not only does it describe over what sort of range a variable can be used by a given name, but there's also a related concept of variable shadowing. So when you go from a big scope like global to a more restricted scope, i.e. when you change scope blocks, as they're called, you can shadow a name, which means you can have another variable with the same name that is not the same variable. It does not refer to the same memory. So if rather than just setting myint to 4, I create a new integer myint here, I say the declaration again, that will compile just fine. But when I run it, I get 0 from inside my function, the getVector function, and the version inside main has a value I consider correct of 4. And the reason is because in here I've shadowed the global variable, and up here I'm using the global variable. So in here, when I'm setting it equal to 4, I'm setting this local variable equal to 4, but up here I'm reading this global variable. Fine. This is something you should be fairly familiar with. But the thing you might be slightly less familiar with is that in C++, almost anywhere you have curly brackets, there are exceptions, I believe, but almost anywhere you have curly brackets is also a scope block. So I'm going to create an int, myInt, which is 1 up here. I'm then going to put curly brackets around here. That line now does nothing interesting. And I'm going to print myInt in there. And close the curly brackets. And I'm now going to print myInt again. And I compile that. And I get 4 and then 1. And the reason is because these curly braces, even though they're just sitting here doing absolutely nothing, they're not attached to an if, they're not attached to a try, they're not attached to a for, they're just curly braces sitting on their own, they've specified a scope block. And inside this scope block, I can define a new variable with the same name, which shadows this myInt. It is worth pointing out that scope is inherited. So in the same sense that I can access global scope from any function in this scope block, if I take that int out, so I'm not shadowing, I'm not creating a new myInt variable, I'll get 4 and 4 because I still have access to this outer scope inside main, inside these brackets. I just also have my own scope block as well. And that's basically what's happening in this try-catch thing. These curly braces here on the try specify a scope block. So essentially, I'm left with this situation. So let's uncomment this so that you can see it again. Get rid of these integer things, which aren't really that interesting. But this is the point. So in this try block, you wind up in one of two situations. Either you've got a variable defined outside here, this version of demo, in which case it has a valid existence. In order for this definition here to sit here, it has to have a valid existence. You have to be able to create one of these objects. It's worth pointing out that sounds ridiculous, but there are objects that can only be created in specific ways, can only be created by other objects. References are a classic example. You cannot have a reference variable just sitting around not currently referring to something. When you create a reference, you have to say which variable you are referring to. But anyway, so out here you have this variable. It has been created. It exists. I do whatever I want to it. I jump into the try block, and if during this function call, let's just go back to the version that's actually like that. If during this function call, this function throws an exception, which it will here, then the assignment, the return effect, effectively, the change to the value of demo just will not happen, because it'll, inside this function, it'll go, actually, this has gone horribly wrong. It'll return out. And rather than executing the left-hand side of this, excuse me, it will jump straight into the catch block. So demo is just left unchanged. If, on the other hand, I have the version which has the definition, i.e. I am, and this I should say I didn't do before, I commented this line out, but I don't have to, because I say this is a scope block, so what I'm doing here is shadowing this demo. But this only exists inside this try-catch. So it doesn't matter that it can't successfully create this object because this never returned anything. Because it never tries to. This causes an exception and immediately again jumps to here, which is outside this scope block, and hence this thing just doesn't exist. And that's the reason why you cannot return or fail to return from a function. So for example, if you're in a function in C++, and you decide, oh, I can't actually return the thing I'm meant to return, you still have to return something unless you throw an exception. Because if you don't return something, then it is not well defined what's going to happen to this object on the left-hand side. And if something can't be well defined, then in C++, it's left as undefined behavior. And once you've reached undefined behavior, you can't know what's going to happen, so you can't do it. On the other hand, exceptions are extremely well defined what's going to happen, which is before anything happens on this left-hand side, you jump straight to the catch block. So either the object never exists if you define it inside your try, or if it does exist, it's never been modified by this assignment. And there we go. As I say, we knew what it had to do because it would be completely useless to, exceptions would be severely depowered if you couldn't raise an exception from inside a function that returns a value. But once we thought about it for a few seconds, it was just a case of, well, yeah, okay, it's got to work, but why? And we spent a bit of time reading the standards and looking through things, and, well, basically, this is why. So, we'll be back soon with another video.